In the last few videos, what we've talked about is sort of the microscopic and the macroscopic connection between different kinds of circuit elements, resistors and capacitors and so forth. In this set of videos, what we're going to do is we're going to talk a little bit about the macroscopic only sort of perspectives on these circuit elements to really get a sense of how we might use them in engineering design, for example. So the first thing we're going to do is we're going to build a circuit. And so we're going to draw a circuit diagram. It has a battery, which has some potential difference across it. We'll call it delta V bat. And it has these two resistors in it, which we indicate with these sort of squiggly lines. One of them we'll say has a resistance R1, and one has a resistance R2. In this configuration, where you have just one loop like this, and the resistors are sort of one right after the other, we call this series resistors. So they are in series, or they are thought of as being sort of one following the other. Now, in this situation, you'll have some amount of current that flows in the circuit around the loop, and that current will be the current I. Now what we're going to do is we're going to apply our ideas of charge conservation and energy conservation, so our sort of fundamental principles, to this circuit situation to see what kinds of things we can extract to understand what's going on in this circuit. So we'll start with this idea of charge conservation, so namely that the total charge associated with a closed system cannot change. This indicates to us that we have whatever current goes into some location has to be equal to the current that goes out, meaning that the current in any part of this really simple circuit is just the current I. So the current that goes through the battery, the current that goes through all the wires, through the resistors, is all the same. Now, in addition, what we're going to do is we're going to use this idea of energy conservation in this system. And namely, we're going to use the idea that the energy is conserved per unit charge. So we did that earlier in a couple of the other videos where we looked at the change in the potential around this whole loop. And that is our statement of energy conservation in a circuit situation. So we're going to look at what is all the energy usage in this circuit in terms of the energy per unit charge. So those two things taken together sort of help us understand what the effect of these resistors are when they're put in series, or they're put one right after the other. So what we'll do is we'll start by adding up all the energy. So the energy in the battery is available for use in the resistors and the wires. So we're going to do this kind of explicitly at first. And we'll say that there's some energy that gets used in the actual wires that sort of connect up all the circuit elements. There's some energy that's used in resistor 1 and in resistor 2. Now, we're going to make another assumption here, which is that the wires are very, very good conductors. So the energy that gets used to move charges around in those wires is very small compared to the energy that gets used by the resistors to move charges through them. And this goes back to that idea of a really thick wire and really thin wire. So what we're going to do here is we're going to say that this is roughly 0. And so whatever energy is available, so this source of energy, is going to be used up in these two sinks. That is energy users, right? So these two resistors are, you can think of as energy users. So as a result, what we have is a relationship between the total energy available in the battery and the energy that is used in each of the resistors. Now, how do we write that out? Well, we have to go back to our description of what the potential difference is across a resistor. So if we go back to Ohm's law, we know that the potential difference across any resistor is going to be equal to the current through the resistor times its resistance. Now that's just a model that we have for these kinds of resistive elements. But the thing that we have to take into account here is that the battery is a source of energy and the resistors are sinks or users of energy. And so when we actually put this model in, what we're going to find is that if we follow the way that this current goes, these guys will be introduced with a negative sign, indicating that they are using up the energy in this circuit. So when we go ahead and do that, we're going to end up subtracting off the current through the first resistor and subtracting off the current times the resistance of the second resistor. And so what we have is a description of how the energy is being provided to the circuit, and also how the energy is being used by the circuit. So we can take this up here, and what we'll find is that the potential difference across the battery is equal to the current times the sum of the two resistors. What this allows us to do is to think about what the net effect of having these resistors in series is. Really, that if we wanted to modify the amount of current that we have running through the circuit, what we would have is a given battery will have a different amount of current depending on our choice of these two resistors. So if we want more current, we would choose less resistors. If we wanted less current, we would choose larger resistors. Now the last thing that we're going to do is we're going to talk about a thing that we would refer to as the equivalent resistance. So if we wanted to understand the circuit on a very, very high level, very simple level, what we might conceive of is a circuit has a single resistor, same potential difference across the batteries, but it has a single resistor which is given at the value of R equivalent. And in an equivalent resistance scenario, what we're saying is that we could take these two resistors and replace them with a single resistor and drive the same amount of current. And we can do that if, in series, resistors add just like that. That is that for every resistor you put in series, you will have that the total sum of the resistance tells you about the equivalent resistance. So they add up in series, just in order. Now, we can think about that from a microscopic perspective if we think about the resistors as being essentially just longer, right? Having these two resistors is essentially like having one longer resistor, and the longer resistor from the microscopic perspective tells us that we would have a higher resistance. So what we did in this video is just derive the equivalent resistance of resistors in series, think about how the current is affected as we add more resistors to the circuit in series, and use our principles of conservation of energy and conservation of charge to do those derivations. In the next few videos, we're going to do the exact same thing, but with different kinds of elements and still applying those same principles.